హాయ్ ఫ్రెండ్స్, మనం ఈరోజు పవర్ ప్రొడ్యూస్డ్ బై an reaction turbine గురించి తెలుసుకుందాం. ఓకే, సో దీంట్లో కన్సిడర్ ఏ రియాక్షన్ టర్బైన్ వర్కింగ్ అండర్ ది యాక్షన్ ఆఫ్ స్టీమ్ ప్రెషర్. సో consider a reaction turbine working the action of steam pressure. So let us draw a combined velocity diagram for the reaction turbine. Okay, now already in previous class we see how to draw the combined velocity diagram for reaction turbine. Now also I can draw here. This is VB. From point B to go the point C, and then C to A. So this is called V, and this is called, we take VR, and then here I draw exit velocity point D. Now this is the inlet velocity diagram, this is the outlet velocity diagram. Then two lines like this. Here also I draw. Okay, now this point I take E, this point is called F, we know this is VF, and similarly it's called VR, it's called V and VF. So already here we take V, so then here I put it 1. Now this here you can see well velocities. Now here it will come angles. Okay, I take this is alpha, this is theta, and phi. Now here we go for beta, like that. Okay, so this is the velocity diagram for reaction turbine. Let M is equal to mass of the steam. Mass of the steam following through the turbine in kg of seconds, and VW plus VW1, that is equal to change in the velocity of wheel. Okay, in meter per seconds. We know that according to the Newton's second law of motion, force in the direction of mean of the blades f of x is equal to mass of steam following divided by second into change, okay, in the velocity of wheel. Okay, then here force F is equal to m into VW minus of VW1. Then we can write this m into VW plus VW1. I put it here, equation number 1. Then you can write down here into E to F VW1 plus VW plus VW1. I can written here EF. So units is newtons, we know very well. Now, and work done in the direction of motion of the blade. So in the direction of motion of the blade, that is equal to force into distance. Then we know very well force is equal to VW1, okay, into VV. That's you can write down here. This is called EF into AB. This is Newton meter per seconds. Look at this. AB is VB. Okay, and now we go for power produced by turbine. So therefore power produced by the turbine. So then P is equal to m into VW plus VW1 into VV. So this is coming from watts. So since 1 Newton per meter seconds is equal to 1 watt, okay, now similarly we can find out the axial thrust on the wheel, which is due to difference of velocities flow at inlet and outlet. So mathematically axial thrust is So we can write down here, we can find out the axial thrust on the wheel, okay, which is due to difference of velocities flow at inlet and outlet. Mathematically, axial thrust Fy is equal to mass of steam flowing per second into change in the velocity of flow. So then here m into Vf minus Vf1, that is equal to m into Ce minus df. So this is newtons, okay. Look at in here, Vf is Ce, Vf1 is df, okay. I put it in here, okay. Now here we take one note. In equation 1, the value of Vw1 is taken as negative because of the opposite direction, okay, of Vw with respect the nozzle action, okay. So that is the reason we take here the velocity, you can here put minus, okay. Now we go for degree of reaction. Now then here degree of reaction. So we have already discussed in out that in a reaction turbine the pressure drops takes place with the fixed and moving blades. In other words, there is an enthalpy drop in both the fixed and moving blades. So we can see this thing first, enthalpy diagram. Now here I put entropy. Now I take this enthalpy I draw the diagram, pressure, A, B, C, H1, H2, H3. This is coming P1, P2, P3. Okay. The ratio of the enthalpy or heat drop in the moving blades to the total enthalpy or total heat drop in the state is known as degree of reaction. Okay, so అది ఎలా ఉంటుంది అనేది ఇప్పుడు మనం చూద్దాం. సో దట్ ఈజ్ ఈక్వల్ టు డిగ్రీ ఆఫ్ రియాక్షన్ ఈజ్ ఈక్వల్ టు రేషియో ఆఫ్ enthalpy or heat drop in the moving blades divided by total enthalpy or heat drop in the stage. So this is equal to H2 minus H1 divided by H1 minus H3. The enthalpy drop in the fixed blades per kg of steam given by H1 minus H2 is equal to V1 square minus V square minus V1 square by 2000. That's the kilojoules per kg. Okay, now at enthalpy drop in the moving blades, so H2 minus H3 is equal to VR1 square minus VR square divided by 2000 kilojoules per kg. Okay, and now therefore total enthalpy drop in the stage, that H1 minus H3 is equal to H1 minus H2 plus H2 minus H3. Okay, so then we can write down here V square minus V1 square by 2000 plus VR square plus VR square, VR1 square plus B minus VR square. Okay, yes, 2000, right? That is equal to 2 into VR1 square VR square divided by 2000. Then here we can write this 2 into H2 minus H3 kilojoules per kg. Okay, since for persons reaction turbine V is equal to VR1 and V1 is equal to VR. Okay, so I know that degree of reaction, that is equal to H2 minus H3 divided by H1 minus H3. Then that is equal to H2 minus H3 divided by 2 into H2 minus H3. Okay, so that is equal to half. That means here 0.5 or 50 percentage. So thus we see that a person's reaction turbine is a 50% reaction turbine. Okay, so this is the calculation part to solve the power work done and enthalpy drops. Now we will see here one problem. In one stage of a reaction steam turbine, both the fixed and moving blades are inlet and outlet blade tip angles if 35 degrees and 20 degrees respectively. The mean blade speed is 80 meter per second. At this steam consumption is 22,500 kg per hour. Determine the power developed in the pair. If the specific heat drop for the pane is 23.5 kilojoules per kg. So, okay, this is the given problem. Now we are going to see how to solve. Solution given. Okay, we take first given here is theta is equal to is beta, that is equal to 35 degrees, and then pi is equal to alpha is equal to 20 degrees, and blade velocity is given 80 meter per seconds, and m is given what is that m here? 22,500 kg per hour. So then we converted into kg per seconds, we'll get 6.25. The heat drop HD is equal to 23.5 kilojoules per kg. Now here I draw velocity diagram, compound velocity diagram. This is given for 80. Now this angle we take 20 degrees. Okay, and now this here take here 35 degrees. This is 35 degrees, this is 20 degrees, and now this point is C. Now here also 20 degrees, here also we take 35 degrees. This is given. Okay, and now we know very well this is VR, this is V, and this is VR1, and this is V1, and this is VF1, F, E, D, now here VF. Okay, so go to here again, will. Okay, so this is the velocity diagram we know very well. And now go for here VW1 is equal to 235 meter per seconds. Okay, we can solve you take this diagram, this triangle ACF. Okay, you can find out here this length. And now here we go for BDF triangle, you get the VW1. So once you calculate this both, we add VW plus VW1, that is equal to 235 meter per seconds. It will come. మన ప్రీవియస్ ప్రాబ్లమ్స్ చాలా వరకు ఇలాంటివి చూసాం మనం. ఓకేనా, ఏం లేదు, ఇక్కడ ఒక ట్రయాంగిల్ తీసుకున్నాము. we take first triangle BCF and second triangle BDF. Here we get VW, here we get VW1. Okay, right? So okay, now you get it now. So we know that power developed, we know that power developed in the pair. So P is equal to M into VW plus VW1 into VV. So substitute all values in here, we will get answer approximately 0.5 kilowatt. Okay, this is the procedure to solve problem. We will see some more problems in next class. Thank you.